So I will give you a few seconds to do this.
And to register.
Yeah, you can also skip it if you want. So we will gather this information and we will use it in later presentations or that kind of things. All right. I will see that still people are filling it in. Okay, that's great. So please continue. I will also show the next question. So did you already play the game that we have? So the Holo game. I would like to see your responses. Very interesting for us. All right, at least everyone knows that the game is available, so that's a good thing. The ones that haven't done it, please visit us. It's nice to have you there. All right, so I would like to start with how SurfNet. You all know SurfNet. We are here and co-hosting this event. So we have around 220 gigabits of dedicated capacity to this event here. And we also need to have applications for using this kind of technology. So SurfNet helps those researchers, teachers, and students to work together using ICT. So using the network infrastructure that is available, and also by collaborating with various kind of people and infrastructure. So we wanted to create a demonstration to reach out to researchers, teachers, and those students, to give them an example of interactive, so you can feel, touch, and use specific the technologies that are available. And every participant should be able to understand the use of ICT within within these various aspects that are available in this demonstration. With doing this, we hope to help participants to think about what is available if we're looking at network, video, and also holographic aspects, and to find their own problems within their use of within their how do you say it, area of research, and how to find solutions for that. So we also would like to talk with them about this. And as last but not least, we also like to have a game element which they are able to enjoy. So what is important also for us is that we find collaboration with other parties. So we are experienced and we know a lot of networking, but there are also other parties that know other technologies. So we have been collaborating with research and education community, international NRN partners, and commercial vendors. So our idea was to create a demonstration where we combine various ideas with, for example, high bandwidth and low latency, which is of course something that we can provide, and we think it's very important to show these aspects of the network. Also, future video technologies, where we want to show what is possible with video. We wanted to do it over a large distance, and once you do that from a country as the Netherlands, you easily get outside of the borders. And also, we would like to show something inspiring, so people think about what's happening and how they can solve their own problems. Of course, it should be interactive, so people take a minute to think about what they're doing, and exciting is also very important. So if we combine all these things, we came up with 4 types of technologies at a high scale, and we started with haptic technology, and we combined that with future video and how we should transport that video, and also over an optical network. So these are the 4 technologies that we're looking into. So the plan was to have If we look at the right side, live video recording combined with haptic feedback at that location. And on the other location, so we needed 2 locations, we wanted to have live video playback and a haptic controller at that site. So to do this, we needed some kind of video transport and also an optical network to have that kind of facilities working. So we were searching for partners in this project. And well, we as SurfNet found Shenna available for helping us with the network part. They are our hardware supplier. We also found Poznan PSNC available for helping us with the video part of this demonstration. They are experienced with various kind of video technologies and know a lot about it. And the Virtual Reality Lab of Twente, University of Twente, was able to help us with how haptic control work and how robot arms work. Both parties, Poznan and the VR Lab, are participating in the Visionaire project. And we were happily glad to work together with them in the Visionaire project. So, well, you know that there are many types of robots. You have robots that just walk around and do kind of stuff. But also specific robots like they use in hospitals, or well, they're still working on that kind of stuff. But what we needed here for our demonstration was a robot device that could replicate stuff on the other side. So we came up with this haptic robot device that is able to simulate force and weight. So when you move it, you will and you touch something, you will feel it. But also when you pick up something, it will respond to that. And this robot has 3 degrees of freedom, so you can move it in 3 directions. And because it was network connected, it was a good opportunity to use this kind of technology for our demonstration, because it also gives you the immediate feedback via the network. We wanted to look into the video feedback, looking into future video, where we show new technologies and discuss and compare the various technologies that are available. So we show during this demonstration what is available with looking into future video, and we hope to use the visual feedback that comes back from the other side. So, well, we had the various types of video technologies, starting with HD 3D, which you can get at home these days. So what we did was setting up a 2x 1080 I50 stream, HD SDI, which was uncompressed, streamed via the network, using for approximately 3 gigabits per second. On the right, you can see how it looked, and of course, you needed the glasses for this. So another stream that we were using was the Ultra HD or 4K stream, which is 4x 1080p 60, so 60 frames per second. And this gave us a throughput of around 12 gigabits per second, live streamed from the other location. We also had to compare another stream, which is exactly the same stream, but it's compressed with JPEG 2000, and the stream was reduced to 500 megabits per second. And this is how it looked, and we didn't really see any differences in image quality. But what we did notice is that the compressed stream, it takes some time to compress it and to decompress it. So you really did see some noticeable delay, while you didn't see that at the uncompressed stream. So what we also had was a holographic feed, or a holographic simulation, and we also used the same video feed for that. And what we did, we had a screen that was laying flat, and it was lifted up a bit, and we had a foil that was reflecting the image that was on the ground, and it gave a really nice perspective. I think if you haven't seen it yet, please visit us in the booth. So we also had the Ultra HD 3D video stream, which is 2 times 4K or Ultra HD. So we had 8 streams of 1080p 60, and it was uncompressed around 24 gigabits per second, streamed live from the other location. And on the right you can see the huge beamers that were installed by PSNC, and it was pretty difficult to really set it up right, because the 2 images should be exactly on the right position to see a great 3D image. And we also used 2 cameras on the other side to record live the stream. So to transport all these types of video, you need, well, you can compress it and send it via the regular internet connection. But we chose to look into something different, and well, we looked into how you can transport with low latency and make sure that all channels are in sync. We didn't choose the compression because we wanted the quality and we wanted the low latency. So we came up with the video motor card from Shanna. The card has 2 line ports, which makes it possible to send around 20 gigabits per second out. And there are also 12 client-side ports, of which 8 are able to directly input or output SDI video feeds. And 4 of them are able to send an Ethernet stream. And it will all be sent over the line ports. The card has a limitation where it's able to, at the same time, get 10 gigabits per second out and 10 gigabits per second in. So the video setup that we used looks like this. On the right you see the 4K cameras and 2 or 3D HD or 2 cameras that were sending a video signal towards the video motor devices, the Shanna devices. And at some of the output we needed converters because they were not outputting the BNC or SDI connections. We also had some of the feeds to the compression, which was connected to a switch, and then connected to a Shanna. And on the other side, it was a reverse option where we outputted all the signals, but we had multiple video feeds showing from the same feed. So, for example, we had 2 of the beamers connected to the 4K streams, and we also needed, for example, the holograph, which required the same 4K feed. So that was an issue for us because with the hologram, you notice that the image needs to be flipped vertically. And since the beamer requires a normal feed, we needed to swap it somewhere in the setup. So PSNC came up with this solution, where we on the left side have the original image. It was mirrored over the horizon, which gives you a horizontal flipped image. And after that, we did a rotation, which gives you eventually a vertical flipped image. And this way, on the video, on the beamer, which has the opportunity to do some flipping, we got the normal image, or the image that you want again, while on the holograph, it's optically flipped. So this is how we solved this. Some locations, we needed to find a great location for this demonstration. So we were looking where we can stream this. So we were in contact with PSNC, so that was the best option. And they were able they had a DWDM system available from Hamburg to Poznan, and we had the same thing from Hamburg to Amsterdam. So that was easy. And we wanted to show a cutting-edge network over a large distance and through different domains. So that was a great opportunity for us. So we set up an alien wave, which uses one wavelength, all optical without any regeneration. And because we do this, we have time savings, so the latency becomes very low. But you also have cost savings because you don't have to buy other cards in for example, in this case, Hamburg, to regenerate, and it also saves power. So that's a good thing. Interesting is so that we go to different hardware, and it's 2,000 kilometers, so it gives us a very, very low link latency, and you will not notice it when you're playing or where you see our demonstration. So for this, we use the Shanna ultra long haul cards. So I want to ask you another question. So do you see the advantage of high-speed network for these types of visual applications? So I'm glad most of you are. And if you have any input for us, you can write it down. So I wanted to, right. All right, thank you. So I wanted to show you how the network setup looked. On the right side, you see the video motor cards, as I just explained, and all the video equipment is connected to this. On the left side, we have multiple 10 gigabits, and it's merged into the 40 gigabit ultra long haul and transported over to the other side here in Maastricht. All of the 10 gigabit streams are demultiplexed from there, and it's directly outputted on the video motor cards. So you also see a video or a connection here between Maastricht and Ottawa. This is because the guys from Shanna at this time also want to show their people the feed from Poznan. So it's an extra part of the video stream that's forwarded there. So the complete setup looks like this. On the right, there's the two cameras outputting 4K. There are two cameras outputting HD. Everything is connected to the video motor cards. For the compressed stream, we have a splitter that here gives some compression, and it's sent over to the other side. And here we have the 4K 3D screen with the silver screen. Also a splitter for here's the splitter for splitting the signal to the 4K hologram and the 4K 2D stream, and also the 4K compressed version is splitted here for the into pics. So another question. In one word, where could you apply one or more of these technologies in your own research? Well, that's expected. Medical is... All right, thank you. I think so. What we tried is something similar. So we try to give you the leaning tower of pizza. So you're able to put various blocks with a remote arm, the holo on the tower of pizza, and well, you hope that it doesn't collapse. So just some impressions. Here is the holographic part where we were testing. Also in action, some users here. Of course, there's also some hardware in action. These are the video motor cards, if you're interested. So some lessons learned. We think that the availability of networks with low latency and high bandwidth is very important for these kind of applications. You require them. The network is an important aspect. The difference between compressed and uncompressed video is noticeable. So there you have also something you can look into. And international collaboration is very fruitful, as you can see the results here. And so we're still learning about usage. So how can we apply these things in e-health, e-culture, maybe e-education and other real-time collaboration areas. So I would like to thank all the guys that were participating in this demonstration. The guys from PSNC, Twente, Shanna, and my own colleagues. So if there are any questions, feel free.
Hi, you might not know the answer to this, which is fine, because I don't think the Poznan guys do. Do you know what latency is added by the camera and the various screens and displays and possibly the video splitters as well in between?
Yeah, good question. I personally don't know, but maybe the guys from PSNC can answer this indeed. Machi, please.
Yeah, we will try to test it tomorrow. Hi, it's Maciej Głowiak from PSNC. I think it's additional 10 to 20 milliseconds, but actually we don't know, because to test the camera and projector, we need camera and projector to be in one place. So it will be probably done on Monday. So we will see. We will inform in next presentations maybe. But I hope including network is about 20 to 30 milliseconds. Video plus network.
Hello, my name is Roger Bairro, FCCN. Just to complement this, Otto Winter, he's not here. He has a paper on this, on how to measure things, so maybe it could be of some assistance. The second question is, the robot arm goes through the Sienna cards or goes through a different channel?
No, they all use the same optical channel, and the robot arm is connected via Ethernet, also on the video motor card, and it's multiplexed inside the 40 gigabits per second link.
So that card is just a bridge to the
Yeah, exactly. You can say it like that. Okay. Yes.
Okay.
All right. Thank you.
Thank you, Michael, for this interesting presentation. Our second presentation during this session is about low-cost 4K 3D camera for science and research. And Piotr Ostapowicz from Poznań Supercomputing and Networking Center will tell us about this camera. He is an expert in digital circuits technology, especially connected to programmable logic devices, including latest generation of field programmable gate arrays. So, Piotr, please tell us about the camera.
Thank you very much. Actually, I'm pleased to be here, and this is actually the second time for me at Arena. First time I was last year exactly at the Iceland. Very interesting experience. Today I will try to present effects of our work on our latest product. Maybe not product, but project. Let's start. Miniaturized and low-cost camera. Well, we used to work with professional equipment, high-resolution professional equipment. It is often, single camera is often a big-sized one, and it is not comfortable in some scenarios. we would like to use miniaturized cameras, and also, what is very important, of course, professional equipment is expensive, but we can do nothing with that because professional staff must have a high cost. But that was the first spotlight on our project. We would like to build something miniaturized. The second one was connected, second spotlight was connected with the electronics market, because you can think what you want, but actually you have to admit that market of handhelds, of portable device, is in constant rush, something like constant rush. Someone put their LCD display. Right now, at the moment, we can find handhelds with extraordinary resolution displays. The same with cameras. Once someone put their camera, today we have, for example, Apple iPhone 4S, which has a camera that actually can produce picture of about 4K resolution, and that's true. That was the second crucial information for us, and we decided to build a small camera, but what is very important with advanced features like professional HDSDI streaming for video. We actually got in touch with producer of sensors, and after some negotiations, we were able to buy some set of sensors for our products. We got a documentation, and the project of miniaturized camera started to be sensible for us. What is very important that there were no approaches for building a camera of such camera. Actually, you can find something like GoPro, like CCTV cameras, but the basic goal there is compression. We don't want to use compressed stream. Actually, we are interested in using stream unaffected by compression algorithms, etc. So we started the project. Of course, there are technical goals. There are technical assumptions for our product, and the first one was to build a small device. It should be small. We didn't want to build a yet another big device, because that is not a challenge. We would rather use or build a small one. It should have at least 4K resolution. That's right. The prototype version, maybe not, maybe in prototype version, lower resolution would be okay. But the final project should produce stream of 4K resolution, and that was also the assumption for that project. And what is very important, we wanted to keep the final price of the project low. How low? Well, here is a table that actually presents most important costs for our camera. The first one is 10 megapixels video sensors. We got it for about $20. For us, it was like, wow, very low cost. We are going to build a camera for nothing. Of course, that's not exactly true, because there are many other parts important and expensive, like FPGA IC, which costs about $200, and printed circuit board, where we have to obey rules of digital designs, where signal integrity is very important, and impedance control, etc. The final PCB is 20 layered, and it costs about $1,000. The last part is a set of video serializers, because we decided to use external video serializers. We resigned from using the internal serializers of FPGA device, because they will be useful for networking purposes. And the total cost is below $2,000. High or no, if we would like to compare it to a professional equipment, we go to we go to a thing that we go to. I'm sorry. We'll figure it out that actually this cost is not very high. Industrial research, we had to get some knowledge about this technology, how to transfer the data from the sensor to our side of FPGA. We had to check the documentation and check the HDSDI standard, SMPTA documents to figure out how to build parts of internal parts of the camera, what is very important. So that was a part of our project. And here we go, use cases. There are first use case that actually is most interesting for us is connected with conception of combining two devices, two systems, professional system, like for example microscope, connected with camera. In case where camera is small enough, it is very comfortable to connect two systems of two such systems. Another example is 3D recording. What is so special in case of small cameras? We can connect them to keep the distance between the lens adequate to distance between human eyes, which is very important. We also figured out that quality control actually waits for such system, like small camera of high resolution and good quality picture. So at this field also it could be useful. And here it is. This picture actually shows a prototype of our camera, the first prototype. We always used to design two versions of devices. First is for proof of concept, second is for, let's say, glory. This one is actually prototype, the proof of concept, let's say. It uses smaller FPGA device. And actually there is the same sensor which was used in Apple iPhone. So here it is. And actually when I will be talking about camera in the rest of the presentation, I will be talking about the prototype version, because final version actually waits for deploying. We wanted to use the modular model. What is very important for us is to keep the sensor away from the rest of the camera, because in that way we can easily change the sensor and actually go to another better quality device. What we can see, what we can tell about this device, actually in the middle of the printed circuit board, there is a Spartan 6 FPGA, the last family, the smallest one actually, but enough to produce HD video stream. There is a streaming header and the place where we actually put the sensor board. And this set is good enough to produce HD picture, using, of course, HDSDI serializer. I know that internal architecture is boring for most of the audience, but I have to say a few words about it because it is a little bit interesting. And we had something like multiple different mechanisms of configuration. There is a sensor which has to be configured. There are another parts, and there are different ways to configure them. We decided to unify the methods of access to configuration mechanisms using typical address bus. Actually, it is very similar to access model proposed by ARM Corporation, but we didn't want to use mechanisms or systems proposed by Xilinx. We decided to use our own system, build it from the scratch, and actually it works very fine. Top-level block has a very easy way to communicate with other blocks to configure them, and that was great and works very fine. On the top-level block, we have to consider the top-level block should be considered as PC, or the block that actually is communicating with personal computer. because on the first stage we didn't use HDSDI, but USB connector to present how the screen grabbed on the FPGA part looks like actually. And here it is. Those are main blocks of internal part of the camera. On the front we have acquisition IP core, actually, which is responsible for grabbing the data from the sensor. It uses differential pairs and high frequencies, and double data rate technology. And actually it worked fine, very fine. Second block is the mosaic block. Each sensor has a pattern that actually has some missing parts of color components, and of course there have to be a block that will use that will reconstruct the missing parts, and also it works great. The third one is buffering block, because we have two different clock domains. There are two frequencies of clocking. The HDSDI streamer part is clocked by a different frequency than acquisition IP core, and thus actually lead to a requirement of something like compensation block. And here it is, buffering block, it works fine also. And the last stage is HDSDI streamer, which is responsible actually for producing the final video stream using SMPTE 292 standard, and also it works fine. Video issues. Actually, I would be lying if I said that actually there weren't no problems with video. There was. I'm sorry. I am not asking what actually this picture presents and if it is corrupted, because it is perfectly fine. It is the first picture that we got from our camera. It presents the test pattern that is generated by internal logic of our sensor. Well, of course, you can say that there are some artifacts on the blurred boundaries, but that is not important. The reason for that is because we made downscaling before the debarrization part, and here it is. Most important in that, on that slide is the histogram. Actually, you can see that this picture is presented by multiple values of color components, red, green, and blue, and everything is correct on that picture. And another one is the proper or final this stream, that the picture that was produced by correct streaming from the camera. Actually, you will never know what it presents. To be perfectly honest, it is a box of coffee from my colleague's desk, and that's the reason. Actually, the real picture was presented by only few values of color components. And it is obvious that actually that was caused by misconfiguration of internal part of sensor. What is very sad is that actually vendor engineers admitted that fact, but unfortunately there is a lack of communication between us and them. We have to use contact or contact indirectly by using local vendor distributor. That is actually the last part, last problem that we have to solve, and we know that it's just misconfiguration. So each other thing is actually working fine. What are the limits for selected models? Where first of all, we are using 8 lanes of data transmission lines, which lead to 8 gigabits max per second, and that is enough. But for future application, we have to think about other solutions. But for 4K, it would be enough. MIPI controller. MIPI is an approach for standardization in case of tiny little stuff for handhelds, and I think that MIPI control implementation should give us in the future better results. We'll see. Of course, with our main board, we are able to connect the professional ASPC sensors, but we will go to another product that actually misses the main assumptions for that, because it would be expensive. It will be similar to the professional equipment, and that's not the point, actually. And that's it. Right now, we are waiting for production of printed circuit boards of final product, and we'll see how it will be. So thank you very much. That is all about our project for now. If there are any questions, please feel free to ask.
Hello, me again. When can I have 3?
Excuse me?
Can I have 3, please?
Of course.
Good. Are you going to be producing many more of these? Do you think anyone would ever take them on board as a product?
Well, we are going to, but right now it is a scientific device or at stage of the research. Okay, we will see how it will be in the future, but right now it's hard to say.
Okay, it's very promising.
Hello, I'm Szabolcs from NIFI, Hungary. Do you have an estimate of how big the actual device will be, including the casing and power supply and everything else that I can take in my hand and use it on its own?
I think that it would be fitted into a case similar to GoPro device or CCTV camera. That is the worst possibility, because we want to make something smaller. That depends on materials for the case, for the housing, actually. But it should not be bigger than typical CCTV camera.
Do you have any estimate on the power consumption? So how long can it run off of, say, a set of batteries?
That is actually a good question, because it should run from battery, like LiPo battery. We don't have the final device. Serializers are hungry for the current, that's true, of course. But I cannot give you the precise answer for that right now. We have to measure that, etc., etc. But it should work from battery for a couple of hours, I think.
Are you planning this camera to make this as an open hardware project?
I think not. We use our proprietary IP cores, so that's our invention, and I don't think that we will try to open it. So. Well, thank you very much.
Thank you very much, Piotr, for this interesting presentation. And our final presentation during this session will be done by Domenico Vicinanza from Dante. He works at Dante, as I said, at Cambridge as a product manager. He received his Master of Science and PhD degrees in physics, and he is a professional musician. And he will tell us about the framework for analysis of medical data using the sonification across JANT network and the European grid infrastructure. And this presentation will focus on how advanced research and educational networking and grid computing could help making a difference in the field of epilepsy diagnosis. Domenico, please.
Thank you very much, Bartek. Ladies and gentlemen, good afternoon. Thank you very, very much for being here. My presentation will focus on a particular experiment, a particular collaboration we started with the pharmaceutical institute in the field of neuroscience, trying to understand whether it was possible to bring to the hospital or to the research centers grid computing and algorithms to deal with epilepsy diagnosis, and in particular using a special way of analyze and work with data. In this case, the translation of data into melodies, into music, so data sonification, and to see whether this could actually make a difference to the researchers, to the neuroscientists, and offer a possible better way to support patients. So I'll start immediately giving you a brief overview about what data sonification is. So how does it work? What are the benefits? Why we are actually why we decided to work together with researchers in using this particular way of analyze data, and then I'll go through the technical steps that we followed to bring the actual computation and the algorithms to the hospital where the researchers are, and finally a brief analysis of the results. So let's start with sonification. Data sonification is the representation of data by means of sounds and melodies. So instead of just using points and lines on a graph, what we're using is a set of nodes, and we are using melodies instead of lines to represent information. So this is something that we did last year that was pretty successful. We started from the data published by CERN at the time. That was the 4th of July 2012, when CERN made the announcement of having found a Higgs boson-like particle, and you can see this is the data proving this evidence. So you can see this bump here, which represents the evidence of the Higgs particle. What we did was taking this data from CERN, converting them into a melody, and you can see the same bump here being represented into the score. And we can actually, so in this way, we can actually create a real score, create a real partition that any musician can play. And for example, this is how it sounds like played by a piano. So you can immediately see what are the potentials of this kind of investigation. So let's do a step back. Let's try to understand first of all how this conversion works and why we are doing this conversion. So why we decided to use music to represent data instead of just plotting as all the standard researchers or human beings do. So sonification is, as we say, a conversion of data into music. So it's basically associating to each single value, numeric value, a note on a score. And this is valid, and this is perfectly doable, provided that two conditions are met. The first one is the uniqueness. So the same value needs to be associated to the same note. Let's say, imagine that your measurement instrument gives you 25, and you decide that 25 is middle C in the score, in the piano. Every time you have 25, you play middle C. The second condition is called covariance. So the melody needs to vary as quick as the data, so that they're actually providing a meaningful, truthful representation of the variation of the data. For example, you have 25, 26, 27, and you represent those data by, let's say, a series of notes like C, D, E, so that they have the same degree of increase or decrease. And let's just have a look at an example, for example. So imagine that your experiments gives you this series of numbers, like in this case 10, 15, 15, 10, and so on. And let's just imagine to use, let's say, higher nodes to represent larger values and lower nodes, so lower pitches to represent smaller values. So this can be, for example, a score that can be generated using this kind of idea. And as you can see, for example, you have 15, 15, and you have here the same point. So you have 10, 15, 15, 10. Let's go a little bit further. Let's say your data have some special property. So in this case, for example, the data we have is showing a periodicity, a regularity. Every certain number of points, it repeats exactly as before. So we have a module, and this module is repeated, basically. So how does the melody representing this data will look like? Doing exactly that, applying exactly those two rules. Something like this. You see the melody inherits exactly the same regularity. You see that second half here is an exact copy of the first half. And we can listen to it, and we can actually recognize the two modules that are the same and are repeated. And so on. So we can listen to, so using the music, we can actually listen to the symmetry, the properties of the original data, just using the ears instead of using the eyes. So, but what are the advantages of the sonification? So, what is bringing, what are the new things that sonification can give us that we couldn't have from data represented as a graph, for example? Well, sonification representation are particularly useful when we are dealing with pattern recognition, with understanding, for example, transition between different behaviors, like a regular one or a chaotic one, or they are really useful when we are representing complex data, because the sound can pack a lot of information in it. We can use the timbre, we can use the volume, we can use the position in the space, we can use the pitch. So there are many information that can be packed, compressed in a single sound. And that's a great thing. So, and higher, well, for example, representing something that has more than 3 dimensions is a little bit tricky. The other thing is that the eyes are really good in giving us at a glance view, a snapshot of something. So we have a global view, while the ears are really good in doing a sequential analysis. So the thing is stream as a train of information and processing them. And for example, it is quite difficult to distinguish a light which is flashing under 20 or under 50 times a second, while it is really easy to distinguish a sound which has under 20 or under 50 hertz. So there are some properties that the ear can deal with in a better way than the eyes. They are naturally trained in distinguishing some properties in a way that the eyes find a little bit more difficult to deal with. So what are the and the other great thing of the eyes of the sound is that it's not directional. So we don't have to stare in front of a monitor to get to look at our data. So to get information from our data, we can wear our headphones and we can just go around, do shopping, jogging, and listen to the data that are coming. So that's a pretty useful information. So looking at the applications of the sonification, there are many of them, from monitoring to training, from data analysis to artistic performances. There are 2 main categories we can actually group. We can actually group all the applications. The first one is related to scientific data analysis, so to provide a different perspective to the data that we analyze and we study. And the second one is an artistic one, so we can use data sonification as an inspiration, as a way to inherit from the richness of the data, and actually have a new way of creating scores, of creating art. In this specific case, we are analyzing a scientific application. But for example, if you go in the lobby here, there is a so the poster number 15 is displaying an artistic interpretation of the sonification, taking data from the space and converting them into melody. So that we have both of them, and we are working on both of the aspects. So scientific application. Our scientific partner for this study is a non-for-profit biomedical organization working in the field of nervous and mental illnesses, cancer research, developing new drugs, and studying how to improve the existing drugs for those diseases. Actually, the researchers they decided to work on one particular nervous disease, which was the epilepsy, for several reasons. First of all, because according to the World Health Organization, epilepsy is the most common serious nervous disease. So it gives us quite a lot of statistics. It's quite a lot of lot of relevance and a lot of urgency in providing alternative way of diagnose and treat epilepsy. Epilepsy is a brain disorder, and epilepsy happens. I'm oversimplifying, of course, when a cluster of neuron is giving a wrong signal, and this is normally observed through strange sensation, strange emotions, violent muscle spasm, convulsions, loss of consciousness, and even if there are many possible causes, and actually there's a huge variety, unfortunately, of causes that can trigger or that can lead to this disease. In many cases, the cause is still unknown, so it's really difficult to diagnose and to treat epilepsy. And it's really, really ancient disease. The first time we hear about epilepsy is more than 3,000 years ago. And I have just a few statistics about the disease. I only would like to stress a couple of numbers, like this one. So 1% of the population in the world is affected. So we are talking about a disease affecting 50 million people in the world. 90% of them are in developing countries. And have this number in mind when we are going to talk about network and going to talk about the involvement of research and education environment networking in this particular study. And unfortunately, a quarter of patients is not responding to conventional drugs. So there is still a lot to be done to improve the life of the people affected by this disease. Many famous people were affected by epilepsy, Van Gogh, Alexander the Great, Julius Caesar, Lord Byron, and many others. So the diagnostic tool the researchers in this study are using to diagnose epilepsy is based on what is called an electroencephalogram, which is a record of the brain electrical activity. So it's something looking like this. So you have many lines, because typically this information is collected by a cluster of detectors that are placed around the scalp. and from the EEGs, the physicians, the doctors can detect when something wrong is happening by inspecting, so by looking at the graph. So our study in this case was supporting those researchers to try to understand whether converting this a digitalized version of the EEGs could be used, and using sonification, so converting this digitalized series of data into melody, into music, could help the researchers to find a baseline or some marker to have an early diagnosis, or to have a way to forecast an impeding seizure, so an impeding attack, and also to find new way of investigate and find new therapies. So this was the scientific background. Let's see how the technology helped in this study. So in particular, how the research and education networking, grid computing helped to build the right infrastructure, and how we use this technology to bring algorithms, to bring computing power where the researchers were. So the role of research and education networking and computing was to actually help creating the actual computing infrastructure. And we needed high performance computation, and we needed grid computing, because if we were just using standard PCs to analyze just a few megabytes of data, that would have required something like, say, a few hours on a standard laptop, on a standard PC. While in this case, using a distributed grid environment, we could actually parallelize the task, and just after a few minutes on the grid, we got the result. And I'm talking about reliable networking for two different reasons. The first one is because reliable networking are the basic ground layer on top of which the grid computing infrastructure we use, the EGI, so the European grid infrastructure, is built, but also because thanks to the reliable networking, we can actually bring the computing power where we need. And our main task here was to bring the computing power inside the hospitals, or where the researchers were and where the data is produced. So let's see how the actual scenario looked like. We have the hospital where the data is recorded and is produced, and we have on the other side the grid infrastructure ready to, with the algorithms ready to do the computation and to create the melody. The EGI infrastructure is built on top of the GEANT and the NREN network infrastructure. And what we asked the doctors was just to have a browser, even on a laptop or on an iPhone, on an iPad, any mobile device worked. So no software installation, just using a browser. And through the browser, you could upload the data to the grid, start a grid job, and they didn't need to install any software or learn to use any software. Just upload the data, and then the grid infrastructure took care of creating all the right analysis tools and analysis jobs, and create the melodies in the analysis. So just a couple of words about the actual network infrastructure. So we used the NREN network, and we used GEANT. GEANT is the pan-European network connecting 25 European POPs, 40 European countries, 8,000 institutions, 50,000 kilometers of network infrastructure, connecting together with the NRENs 40 million users across 8,000 institutions. Is something quite big, but probably even more important than that is the following picture, showing that outside Europe, GEANT is reaching a total of 62 countries. And this is extremely important because of that 90% of the population affected by epilepsy living in developing countries, and you can see we're covering quite a lot of them. And the involvement, our involvement as a research and education network provider is to help and support, so continuing this process of bringing the network toward all the world's regions, so that we can, through the network, we can actually bring the right tools where the people live and where the people are actually experiencing problem. A couple of words about the actual portal we used. The portal has been developed by the Italian National Institute for Nuclear Physics in Catania. It's called Science Gateway. The idea was to have something that didn't need to be installed, so nothing to install, something based on standard protocols, modular, so that additional plugins could be immediately loaded and used. And for those of you who are interested in the technical details, we used LifeRay as a portal container, and JSaga to access grid resources, and the authentication was based on SAML and Shibboleth. This is how the portal looked like. So this is what the neuroscience researchers were presented when they they logged in and they went to the portal. They could even select from a map a grid resource if they liked. There was also a mechanism to rate actually resources according to their availability or their preference. This is the screenshot of the place where the researcher could actually upload their EEGs, so their files. They could choose whether to also have analysis, what are the parameters of the actual sonification, and automatically, so without having to do anything else, a grid task is created on EGI, and the final result is possible. Well, it was possible to inspect on a map the status of the job. So if the researcher was curious, they could know where in the world their job was executed. And when the job was done, Melody created and analysis done, the data sent back from the EGI through the network directly to the mobile device or to the laptop, to the computer of the researcher who generated the task. And so this is the whole process, so starting from the data and arriving to the actual score and to the actual analysis. And I would like to conclude just giving you showing a few screenshots of the actual analysis results that the researcher could have thanks to this process. The main tool was an animated map showing how the melody generated by the EEG was self-organizing around some tonal center, and working on smart sonification algorithms, it was possible to find a way, or so at least this is what the researchers are doing in collaboration with us, trying to correlate the tonal distribution of the melody with the actual status of the stage of the disease. And the hope is trying to find the marker using this kind of animation. This is just a screenshot of a movie file. Other tools the researchers have are things like this. This is the pitch distribution as a function of time, and they're looking for clusters, for example, and trying to correlate a cluster of nodes or cluster of intervals with stages of the disease. That's another picture showing something similar. Again, this is the frequency of the nodes, and this is the time, and they're looking at things like that to identify patterns or irregularities or anomalies in the distribution of the nodes, and final graph as distribution of the intervals, so the jumps. And if the sonification algorithm is thought or is conceived in a particular way, these intervals can actually tell the researchers quite a lot about the actual stage of the disease. So the occurrence of the interval could be mapped to something quite useful. So it's not just listening to the melody, but it's also there is also quite a lot of work we are doing with them, trying to analyze the data from so using music analysis technique on the actual melody that we get in as a final result of the computation. So summarizing, we use research and education networking to create an infrastructure to offer researchers inside the hospital the possibility to upload their own data, create sonification, analyze the music, analyze the melody, and bring back where the researchers are, where the patients are, the data of the sonification. The researchers decided to use sonification technique because they thought it was the most appropriate way to look at time series and to look at a series of a number of series of information. So visual approach, they say they don't take temporary information into account as the sound does. Our research, of course, is a very early stage. It's kind of first proof of concept, and so the plan is to work even more closely with the researchers to design the right sonification algorithm and to refine the methodology of analyzing the result, creating the right tools for them. But the really great result of this study is the fact that we were able to, so using the research and education environment, using the network and using EGI, we were able to create a computing infrastructure and bring it where the researchers were, inside the hospitals, so next to the patients, as close as possible to where the computing power and the algorithms were needed. And that's my last slide. Thank you very, very much for your patience and for your participation.
Bram Peters from SurfNet. I'm quite intrigued. Do you actually have a data set or something that we can listen to where we can hear what it does with real scientific data? Because I can hear the sine wave, that makes sense. But listening to an ECG or anything, it doesn't make sense to me.
Yeah, so thank you very much for the question. The key point is the actual algorithms we are using to transform the melody into the data into melody. If we have a look at the actual, back to the epilepsy, yes, this one. We can see here, for example, there is this is the phase interesting from the research point of view. So when the actual seizure is happening, and this is the kind of steady state, and this is the status after the seizure. The idea is trying to find the correct mapping between the data and the actual music scale and music intervals that would allow the researcher to listen to the right thing. The example I made with the sinus and the actual regular melody was using a really simple mapping, a linear mapping between the data and the melody. We are using all sorts of mapping here, from linear. We're using exponential mapping, logarithmic mapping that are making really easy to understand big jumps or small jumps, or compressing or expanding the scale. So there's quite a lot of work we are doing with researchers to find the right way of coding into music information, something which is visible here, and also trying to find a way of translating the right information into the melody, so that the melody analysis that we are doing afterwards can actually pick this information in an easy and clear way. This is everything I can say at this stage, unfortunately. So this is.
It's really rough to hear how that works, because to me, I see graphs, I can hear some graphs, you can make any mapping on a graph, make it logarithmic, make it anything you want, highlight the things you want to highlight, but listening to music, when you listen to music, you have I can listen to very complex noise, I don't distinguish the noise in the noise. On a chart, you can highlight things, you can easily sort of bring out the data you have, and it's a similar kind of transformation you do, only that you bring it into a medium that to me is actually quite hard to grasp. I play music myself, I have trouble when I hear an orchestra to distinguish between different instruments. I can hear a melody, I hear when something's going wrong, but I can't distinguish what's going wrong. So it looks like a very unusual, intriguing, but perhaps brilliant way of doing things, but I would like to experience that.
Oh yes, of course, and I absolutely agree with you. It is also something that requires a different kind of training as well. So we're normally trained on looking at a graph and distinguishing or detecting things by looking at a visual representation. We need a kind of we need the same kind of training, listening to to sonic information and trying to understand what is the meaning and what the data are telling us by its melodic or melodic representation. There is also another aspect, which is trying to help blind or visually impaired researchers to do data analysis. This is a parallel field. I'm not even mentioning that because there's a completely separate topic. But we are interested in sonification also for that. So to give the possibility of blind researchers and visually impaired researchers of doing research, doing data analysis, and having access to a kind of data analysis field, which is normally up to now reserved to people that could look at a graph.
Well, I can only share the skepticism, mostly because we all know that music, as we know it, is completely an artificial thing. I mean, and we just perceive it as we do because it's been invented hundreds of years ago and we got used to it. So I don't really see the point of taking natural data, mapping it to something very artificial, and then trying to find out something about that. And this is why I would be interested to actually hear the melody you are doing, and because I noticed that you do this sonification stuff, and basically in the end you see I saw just graphs. So it's basically visualizing through sonification. This double mapping is kind of strange. It's a pity that we didn't hear any really samples.
Well, to answer the question, skepticism is good. It's always good. So skepticism really is what has driven the whole research world from the let's say thousands of years ago to now. So yeah, so that's good. And of course, we are the first one to be skeptics. The reason why we believe there is something more than just an alternative way of kind of just a nice exercise, if you like, is because music is I wouldn't call it artificial. It's quite complex, self-organized environment. Because music has tonality, has scales, has quite a lot in it. It's a really rich environment. And we have quite a lot of tools to work with this rich environment. What we believe, together with the researchers, is that if we find the right way of mapping things into this complex, self-organized environment, we hope that some of the properties will be more visible or more evident than having the same information visualized on a graph. Whether we are right or not is really too early to decide, so we are really at very early stage. And I agree with you. Probably it is also quite useful listening to the data. I thought it was probably showing something different, like so the arrival point was probably more useful. But if you're interested, of course, I'm more than happy to share with you the audio file, and of course I'm more than happy to take on board any suggestions. So this is really an open environment. That's just the first step. And again, any skepticism is really good because it is what really drives us to move to the next stages. So yes, thank you very much.
Hello.
Rui.
First two comments. The first comment is that back in the 60s, computers didn't have screens, and debugging a computer program was difficult. So they associated the speaker to the instruction pointer, and you could hear the program running, okay, and make loops. And when there is a loop, you get some sound very repeating, okay. So this could be revival, let's say. The second thing is I've heard a set of music generated using this, and maybe you should share with us if possible.
Of course, yes.
The third one is the question. Why do you convert only into tones? You know, the MIDI file is just a MIDI file, okay? And this data is much more rich. Why don't you make the, you know, the samples of the instruments and then make them play? Okay, something more.
Sample of the instruments. Sorry, I didn't get the.
The music is synthesized, right? It's a MIDI file. You play a CG while it's playing, but that information is much more rich. Okay, in fact, you could synthesize from that an instrument and then play the instrument.
So the actual.
So instead of making a MIDI file, you could make a WAV file.
A WAV file. Okay, yes, we are doing that as well. So we are doing many things. So we are exploring many different way of analyzing this data. We are working on WAV files as well as, and what we are doing in particular was doing time compression. For example, we're doing really long recording for days, for example, and then squeeze them into a few minutes recording and trying to listen to the actual variation that in this case became really evident. Or if you have some periodicity, some regularity, something happening every day or every night, compressing and listening is a really great way of doing that. So this is an alternative way. So I had to choose something in the huge variety of things we are doing. I tried to choose something a little bit more original. Okay. But yes, I agree with you. I totally sure that that's really useful. Yes.
Thank you for your very interesting presentation. I'm not as skeptic as two of the other people in the room, because in the 80s when we had computer programs on audio tapes and you listened to them, you could actually hear at what point it was streaming code and at what point it was streaming graphics, because it sounded completely different. So I believe this is a very interesting approach. What I was wondering is, you briefly touched on visually impaired people and blind people, and they often say that people that are blind, that the other senses improve, and specifically the sense of hearing. Have you done experiments to see if blind people are better able to train themselves to recognize patterns in these kinds of data if you sonificate it?
Oh, that's a really interesting question. Well, first of all, thanks for the optimism, and thanks for the question. Skepticism is good, optimism is good as well. So, so more seriously, we never had the opportunity of working with blind researchers on this specific topic. So we work with blind people in music representation, so in sonic representation of the data. And we worked more on monitoring purposes rather than data analysis at that time. So, but we are trying to launch a program also involving blind association, trying to involve CERN, for example, to encourage blind researchers to work with us and try to understand whether we can help providing the right tools for them. There is no one size fits all. And we need to closely, we learned what we learned with this project is that we need a close collaboration with the researchers to develop the right algorithms for the right data at the right time with the right specification. So, but it's a wonderful journey. I think it's really great to have the opportunity to work with blind or visually impaired people and giving them the possibility of doing something that was completely out of their possibility up to now. There are lots of research which is done by watching and looking at things that we believe can be done equally better, or so equally good or even better by listening to them and using exactly what you're mentioning. So thank you.
One question. Actually, how good a musician you have to be to use this method of the data recognition, because it is obvious that actually there are people that don't have the skills to hear the sound, you know. Do you have to have skills of musician, and how the skill should be?
Well, That's an extremely good question. Of course, as there are different capability in looking at the data and say, oh yes, I see something really wrong here, and you have the same X-ray picture, and two doctors can see two different things. Hopefully they agree on what they see, but there is different skill that based on the way our senses are working and our brain is working in interpreting the data. This is exactly the same with music. That's something quite basic that everybody can do, almost everybody can do. Like, imagine detecting a wrong note in a song. You listen to a song that you know, Happy Birthday, and you hear a clearly wrong note. You can immediately spot it, even if you don't have any music training. And that's a basic thing. And there are more complex things that, of course, are depending on the level of music education and skills. But of course, we need training, as we need training and looking at the graph and spotting something different or something wrong or something unusual there. So there's a huge variety. There is not just one off. So there is not just a single kind of skill. There is a huge variety of skills that needs to be developed.
I think you just started leading on to what I was going to say. There's a technique in displaying variables graphically where you display them as faces, and the variables change the proportion of the features, and that's exploiting the fact that the brain is very, very good at recognizing and remembering faces and spotting anomalies with them. You've referred to the sort of quantization of the analog data into musical notation as melodies, but certainly the samples you've played aren't actually very melodic. Have you considered an approach of using the data to modulate something that is actually a recognizable tune, and therefore exploit all that training we've all had through our lives to recognize how a tune should go and spot the differences, rather than having something that's very jagged and, Stockhausen sounding right from the start, that's rather harder to interpret?
We did something in that area as well. Not in this study, but in our lab exploring different possibilities. We used, for example, MIDI data coming from this sonification to change a modulation index actually on a synthesizer, so changing and altering or varying the spectrum of the timbre of the sound according to a particular parameter. So, for example, if the temperature of a sensor was becoming, let's say, higher and higher, we got kind of distortion of the melody or distortion of the timbre, and so you can actually hear really quite clearly that's the actual sensor was picking up much higher temperature than before. We did this kind of things for monitoring purposes. I have to admit, I never really explored that for this kind of investigation. So that's something probably we need to do as well. So thank you very much. But technology is there. Everything is there, as you say. So it's something quite widely used. So yes, again, we are really at the very, very beginning.
Thank you.
Thank you.
Thank you very much, Domenico. This was our last presentation. I would like to tell us a few announcements for today and for tomorrow. Demonstrations are in free location during the breaks. Tomorrow, please check the online schedule. And one demonstration is behind the black curtain, so if someone hasn't seen it yet, please go and see. Feedback. Please visit the conference webpage and share your opinion about the conference. Open space sessions. Please share your ideas and votes on Thursday afternoon. And the last announcement for today: gala dinner is tonight. Please bring your badges or tickets. And buses are departing between 7:15 and 7:45 p.m. from the entrance. And the location is in the chateau, so we advise you to wear suitable shoes because it will be also outside of the building. So please wear suitable shoes. Thank you very much for attending this session.